Thank you, Christoph, and good, I guess it's morning still, technically, to everyone. So my name is Johannes. I'm a postdoc at MIT, and today I'm presenting some work that we're doing between MIT and Airbus, and with my co-authors, Shao, who was at MIT at the time of the writing of this paper, Alain, who's our counterpart at Airbus, and Eric, who's at MIT and could not come. And the topic for today are methods for extracting structured data from natural language requirements using natural language processing. And so, to give you a bit context for the problem, okay, there seems to be some, yeah. Okay, I'll carry on. Okay, I see now. It's different. Okay, sorry about that. Yeah, so the context of the problem is that in the natural language requirements that we have today, there's a lot of embedded data that pertains to the system models that we're now starting to have more and more of. So there is a coupling between, of course, the engineering requirements and specifically the data that is embedded in these requirements and the system models. And now, in complex projects, we don't only have a couple of requirements, we have incredibly many of them, 10 to 100 of thousands of natural language requirements for complex engineering projects. And on top of that, there are standards and processes that require that this information is managed appropriately. And of course, this is for potentially one product, but then there might be multiple variants, and then you have to manage that data as well. So what do I mean by data embedded in requirements? Well, let me give you a couple of examples of the type of data that we can find embedded in requirements, and I'll use real requirements from real projects for this. So we can find system parameters, names of system parameters, and quantities. So for example, if we take this requirement here is from a student competition, the total mass of the can set shall be 600 grams plus or minus 10 grams. We have a reference to a system parameter, or just a parameter, the total mass, and a quantity at the end. There might be references to the functions and systems of interest in the requirement. So for example, here's a requirement. It talks about a tank, the main tank in this case, and talks about a function to fill it, and talks about what it's being filled with, the superfluid helium. And these are elements or data that you might find embedded somewhere in your system model as well. And then, of course, some of the requirements, and this might be familiar already given the previous talks that we have had, talk about the temporality of certain things and what type of things need to happen, and talk about events and modes. And so again, these are all requirements from real projects. The second one is from the ESA Herschel Planck, and the third one is from the landing gear case study that we saw yesterday in more depth. So the goal of this paper is to compare structured data extraction methods and how we can actually go and get there. So what are the type of methods that we can actually use in the first place? And so we have divided those into three types. And they all pertain to the information extraction problem that I will talk a bit more about. So we formulate this as an information extraction problem, and then we look at what are the ways in which we can solve this information extraction problem. It's a known natural language processing problem. And then in this paper, we present a very high-level comparison of a couple of different elements to take into account when picking this method, and how these different methods compare in terms of the amount of setup cost, how easy it is to customize to target data structures, and how the methods scale, because as we saw in the very beginning, scalability is very important given the number of requirements that we have. So to give you an outline that addresses these questions, we'll first talk about the information extraction problem. then tell you a bit more about the 3 different types of ways in which we can address this problem, give a high-level comparison of the methods at the very end, and conclude with some outlook in terms of other things that we need to still do. So let's focus first on the information extraction problem and what it is in the first place. And so let's take a step back from requirements, because this is a natural language processing problem in general. And the information extraction problem takes 2 things. You take a natural language sentence, like next to the plant is a factory that makes cars, and explicitly pick the sentence that was not a requirement. Then you have a data model, and a data model consists of a set of categories and relations between them. So for example, here we have a product category and a producer category that are linked by 2 types of relations. And we want to populate that data model based on the sentence that we had. So here I'm just highlighting the populated data model on the sentence. Now, what would this look like for a requirement? Well, in this paper, we're talking about the natural sentence is a natural language requirement, as you could expect. The data model is a requirement or systems engineering-based data model. And then, of course, the task that we're looking at is populating this requirements engineering / systems engineering data model. Let me give you a bit more specific example. So let's take a data model that's very simplified and has been arbitrarily defined, but it has some ideas that pertain to, that come from requirements engineering, systems engineering. Say we have a category we have 4 categories: object, system property, states, and quantity. And we have 3 types of relationships that can exist that you can see up here. And we have a requirement that looks like the following: the nominal air temperature regulated value shall be 40 degrees with equipment state off. So what information extraction looks like in the context of a requirement is essentially what we saw on the previous slide, is identifying the categories within that requirement correctly, and of course labeling the relations that can exist between them. So now that I hope you have a better grasp of what the information extraction problem is about, let me go into a couple of different strategies that we can use to solve this problem. And they're arranged more or less historically or chronologically. So to start with, we'll go into the topic, or one of the ways in we can do it is called shallow semantics. This essentially consists in describing patterns and using those patterns that your requirements, you expect your requirements to have to extract information from the requirement. And so I'll give you an example to be more specific. We take a requirement and we build a pattern that matches underlying information. And the pattern, we can build it with the building blocks of exact words or matches or based on lexicons. It can be based on parts of speech. And these are the word categories that you're familiar with from school, probably, like adjectives, verbs, nouns, and so on. Or they can be, as I said, lists, like, for example, here, a unit list. And then defining rules that once we have matched this pattern, it matches certain elements of that sentence to specific categories. And this is just to extract the categories, and then you can do more advanced analysis to also extract the relations to populate the data model. And so this is just kind of to give you the gist of it. There are more advanced methods, of course. And so on a very high-level perspective, in going back to the metrics that we care about, the setup cost for applying this method is that you need to manually enumerate these patterns and set up the rules. Of course, you can customize this as much as you want, but in general, the number of patterns that you need scales with the number of requirements. So if we're talking about hundreds of thousands of requirements, this is not a very scalable method. I'm not saying that it's one pattern per requirement, right? That would defeat the purpose of this. But it still could be one pattern for X amount of requirements. Now, a different technique takes a step back and says, well, let's just take things that people have done in natural language processing in other domains that are generally English related. And so these are domain-independent methods. So one type of technique that's called named entity recognition has been applied, and models have been trained to do this for specific categories that are so far have been more general in purpose, so names of people, organizations, geographical locations, dates. Now, there is a growing set of more specific domains and higher level granularity models that have been trained. So, for example, product quantity, and here you can see a labeled example. But these are, again, things that you get off the shelf, and they label things based on training data that is most likely coming outside of your domain, outside of requirements engineering. And then there's another technique called semantic role labeling that takes even a further step back, thinks about what are the underlying patterns that we see in English, and assigns categories to the different parts of your sentence based on underlying linguistic theory about English. And for example, here you can see a set of different arguments that are associated with the verb in the sentence. And so these are generic ways, and they give these generic categories, but they're more linguistically related. So the setup cost is 0 here because you have easy-to-use libraries for doing this. However, you have no customization at all, and you cannot adapt it beyond adding, of course, post-processing algorithms, which brings us back to the previous method that I was talking about on the first slide. The last method that I'm going to discuss today, and the most recently developed, is based on deep learning and transformer-based language models. And this is a type of technique that falls under the field of machine learning, where we take a very different perspective when we think about the sentence. And we think about this task of data model population as a task of giving a set of annotated examples, feeding it into a machine learning algorithm with training data, and then hoping that this model will perform well on unseen data. And so recently, in 2018, there have been huge changes in the natural language processing world. And BERT, it's an acronym, which was the first transformer-based language models that implemented a set of technological features, allows to essentially achieve state-of-the-art in many natural language processing tasks. Again, I'm talking now outside the field of requirements engineering. And so one of the big benefits that comes with this is that we can first benefit from having a large set of requirements in order to train, and I will not go too much into detail of this, but the language model itself. And then we have to annotate some of the requirements, but the number of requirements that we have to annotate does not scale with the number of requirements, actually. And that's one of the important things. So this gives us both scalability, full customization, although, of course, it comes with some setup costs. And just to give you a bit more of insight into these transformer-based language models, because that's where we are focusing our research the mostly, is how we can capitalize on them. And as I was saying, we can both capitalize on just having domain-specific data, so databases of requirements without doing anything with them. And then on top of it, the fact that we can leverage a limited amount of annotation that can scale up to a lot of requirements. So what I'm showing on this slide is a pipeline, and I'm going to show the different type of data that goes into this pipeline. And this pipeline essentially tells you the set of processes that you have to go through in order to train different parts of the machine learning model that you want to learn. So we start with some pre-processing, and I will not go into the detail of a natural language sentence. And then we can use a pre-trained language model, and this is where one of the key technologies of NLP come out with BERT is that you can use one model that's been trained on the entire corpus of the internet and Wikipedia to build up an understanding of what language means. And so this model is in some extent, so it's very large, but it's already been trained and it's off the shelf. Then you could feed the model further with, let's say, academic or research papers or engineering reports to give it a better understanding of the specific type of information that pertains to your domain. Then you can go even further and feed it a large corpus of requirements, let's say, so it understands better the type of language that exists in requirements. And again, here there's no work. You're just taking the information that you have already. And then at the very end, what you have to do is an annotation effort, but which again does not scale with the application that you have in mind in terms of large set of requirements. And this is called fine-tuning of the model at the very end. And for this, you need to have examples of the requirements and annotated examples. So I'll just show you very quickly an example that we did specific to requirements, and this is the research that we are working on right now. But this happened since we actually published the paper, but I still wanted to just give you the preview. So for the pre-trained language model, we just used BERT. We explored other ones, but for here, let's just assume we're using BERT that understands English. Then we sourced and scraped a large data set of requirements publicly available, around 41,000 requirements from public data sources. And then we did a set of annotations on about 900 requirements that we took from this corpus that were specific to one data model that we worked with. And the results you can see in this table here, and here we only worked on the category extraction. We didn't work on the relation extraction. So you can see a set of 5 different categories that we worked on related to systems engineering. And the F1 score that you see on the right, higher is better, 100 is the best, 0 is the worst. And just historically, natural language processing algorithms have been performing on the order of 60 or 70. So getting up to 80 or even 90 is state of the art in a lot of other natural language processing tasks. So this shows that these type of models can do really good in terms of replicating the annotation that a human person has done. So this is just kind of a short example, but to wrap it all up in terms of comparison, we have these 3 different methods. There's a 4th one at the top that I didn't cover. So shallow semantics, off-the-shelf named entity recognition, and semantic role labeling, and of course the language-based models. And each have their pros and cons, but we believe that the language models is a very promising one because it has mainly the scalability property that we need for large complex projects. So to wrap it all up, again, we've discussed a set of different methods that we can apply for extracting structured data from requirements. Language models with a fine-tuning layer at the end hold promise for the entity extraction element or the category extraction, and we have some preliminary data that shows that this is doing rather well. But of course, a couple of challenges ahead and still work to be done. We haven't yet worked on the relation extraction part, so that's something that we need to focus on. One of the big questions that we have is what is the right data model for requirements? And then how do we leverage the structured data once we have it for downstream applications? And some of the other things that we've been thinking about is that sometimes the information that you have in a requirement is not enough to do that labeling correctly. You need contextual information that might be other parts in your requirements document. So that's another part that we're working on exploring. So with that, I thank you very much for your attention. Look forward to any questions.
Thank you, Johannes. Thank you very much.